Okay, thank you. Well, good afternoon, everyone. You can probably tell I'm originally from the UK, been in Houston now 20 odd years. So really enjoyed my tenure in SENSIA and Schlumberger and Giscoot and all the other companies that have been acquired since being SENSIA. So today I was going to talk about crude oil sampling systems, specifically around the JetLine technology. I wanted to give you some fundamentals, so I want to try and make this as interesting as I possibly can to you and show you and prove to you how important it is when it comes to measuring quality as opposed to quantity on crude oil parcels and batches, and then go through, well, how do we prove that system? How do we make sure it is working and it's provable? And then specifically jump into the non-invasive jet mixing technology that we're here to talk about, and then open it up, as I say, at the end for QA and discussion. So just to kick things off, just to set the scene a little bit, make it interesting, I hope. 500,000 barrels, which is what, I don't know, 20–25% of the daily consumption of the UK for oil. So it's not a lot. It might sound a lot, 500,000 barrels, but it's not a lot. And most ships, in terms of crude oil shipment containers, carry about 500,000 and up. They're pretty large. But on today's market, I mean, depending what day you look at it, let's call it $50 million. So it's a chunk of money. It's a huge amount of money. And normally when you custody transfer, in other words, you change ownership of that crude, whether you're buying, selling, or moving, either one of the three, you're changing ownership. We call that custody transfer. And it could be in a point of allocation too in the process. But anyway, when you look at that value and that quantity in this example, when you look at the two things have to happen for custody transfer. The first is quantity evaluation, making sure that the quantity that you're delivering, the 500,000 barrels, is in fact 500,000 barrels. But you also need to look at the quality, because it's much harder to see, right? You can measure quantity quite easily in a tank or in a flow metering system. Quality is a bit more difficult when it comes to crude oil because it's all hidden. It's inside pipes or tanks, etc. Now, the interesting thing, which I hope I'm going to explain to you, is the fact of risk or loss, whatever way you want to look at it. But when you change ownership of that type of crude, in this particular instance, typically the measuring standards or the acceptance criteria for quantity is plus or minus 0.25%. And that's typically, I mean, it's not always the case, but it's typical for most transactions. And that represents quite a small number when you look at it in the big scale of things for that 500,000 barrels or $50 million. And the challenging thing with quantity measurement, it can be plus or minus too. So you could lose or you could gain depending where you are on the uncertainty part of that. Now, quality is a whole different story. Quality, depending on how much water, and I'm talking, when I talk quality, I'm talking specifically watering crude oil, because it happens, no matter where you get crude oil from, there will be water in it. It might be a trace, as I'm showing here, or it could be a very large amount, depending where it's coming from in the world and what life cycles it's in terms of hitting the refinery. They might have dewatered it at some point. But my point here is the risk is far greater than quantity because of this water content. If you get a 1% quantity of water in that 500,000 barrels, that's $200,000. That's a huge amount of money, and that's loss. That's direct loss. There's no plus or minus there. You are paying, what you should be receiving oil, you are getting water, and then sure enough, you have to do something else with that water. You can't dump it back in the river or the sea or down the drain. You have to process that water. So there's a huge expense to that, which I'm not even showing here. So in my view, in all the years I've been doing this, I see a lot of people spending a lot of money on quantity measurement, but ignoring quality. Yet quality is the hidden beast in all of this, because it will turn around. Most of the losses in crude oil movements are all about quality, not necessarily quantity. So it is really important, and that's my opening pitch to the whole quality measurement point. Now, in terms of measuring quality, it's difficult. it's not easy because you have to be representative, and that's a big word. It's written all over the standards, and I'll talk about the standards in a bit. But the problem is what you end up, whether you're sampling from a tank or whether you're sampling, a tank movement or a marine transfer or a pipeline, you normally end up with probably a few cc's in your analyzer, whether it be a Carl Fisher or it could be a centrifuge. You'd have a bit more quantity in that. But the turn down ratio from that 500,000 barrels to 1 or 10 cc's, whatever it is massive. It's 1 in 130 billion. So you have to be really, really sure that you're representative from a quality perspective to make sure that that 1 cc you put in the analyzer is truly representative, in this case, of the 500,000 barrels. And that is really, really difficult to do. And from that, you're going to determine the water cut, you're going to determine the density of that product, the sulfur and the sediment, because they're all play into the value of that product, or the risk, as I like to describe it. Now, the standards talk about an acceptance criteria, and the API says it's for 1% of water, you should be within plus or minus 0.15% accurate in terms of measuring that 1%. Well, that's a big number, that 0.15%. That could be potentially a big loss. So, the standards set the bar, but I don't think personally the standards set the bar high enough. The ISO is a little bit better, but in my view and in my experience and the way we've proved it, an approved sampling system can be much, much better than that. It's something like 0.025% accurate for that 1%, which is phenomenally better than the 0.15%. 0.15%, and therefore you haven't got the loss of that 0.15 to the 0.025. So it's significant, but obviously you'd only apply these techniques I'm talking about in the high-end, high-risky applications. If you're producing a couple of barrels a day, you're probably not going to worry about it. But if you're producing millions of barrels or moving millions of barrels a year, you're going to want to worry about this because it's potentially a huge loss. The other issue with the sampling system, the quality measuring system, is it's built up of a number of things that all produce uncertainty. The mixing, which I'll talk about, taking a representative sample from that mixed pipeline, delivering it to a sample receiver, sending it to the lab and analyzing it. All of those things add up to what I call systematic uncertainty. It's not like a flow meter. Well, a flow meter is one thing, one element, one uncertainty. Yeah, the process conditions might change, but essentially it's still the same meter and it's still delivering that same flow reading or flow register day in, day out. A sampling system is built up a number of things that all add up to uncertainty. Now, the standards, just as background information, the standards for crude oil sampling systems, probably the most read is the 8.2. So this is the American Petroleum Institute chapter 8.2 for sampling systems. There's 8.1, there's 8.3, there's 8.4, but 8.2 addresses the automatic sampling systems. And the equivalent to that is the ISO document, which is the 3171. And that's been around for many, many years, as you can see there, but it's currently under revision. And hopefully one day we're going to harmonize very closely. They're very close right now, but very closely, the 8.2 and the 3171. So these are the important standards for bedtime reading that are good reference points, I believe. And I sit on the whole of Chapter 8. I'm chairman of Chapter 8 for API, and we're actually starting our spring meetings this week. So it's interesting stuff. But they're very good reference materials. They've been around a long time and carry a lot of weight in terms of their standard practice recommendations. So let's look at the fundamentals. I've broken it down to 5 easy things. Firstly, as I said on my chart there of uncertainty, mixing, taking a representative sample, handling it properly, running it to the lab, and then finally proving to see you've done your job right and it's actually producing the numbers that it should be doing, and then you can understand its uncertainty. So mixing in a pipeline, right? So pretty obvious stuff, but I think it's good ground rules, right? And hopefully this is, as I said, of interest to you. So water is always going to be, in 99% of the cases heavier than the oil. It's going to be sitting on the bottom there of the pipeline in most cases, especially in marine custody transfer applications or tankage. When you start moving a tank, everything is pretty stratified. It's been sitting there for a long time, so it's not well mixed in the tank or the ship. And then you're moving this oil, and you're probably moving at low velocity to begin with, which is when you see the most water in terms of quantity. And what's happening here is we're taking a sample from that. I don't know if you can see my mouse here, but we're seeing the sample being extracted there from the center half of the line, and then it's being delivered into the receiver. But what we're sampling is the oil, not the water. So it's not representative. You're not doing it justice at all. So we have to mixing. Mixing is one of the most important things when it comes to representative sampling, because it's the hardest thing to do. I think grabbing the sample is just it's a mechanical device, pulling a sample out, or you could put an analyzer in there, right? Like an online water cut. But unless you've mixed that pipeline, you are not representative. Therefore, the value of your quality measurement is useless to you. It's just not meaningful. You're missing the bad stuff. So when it comes to mixing, what are the important things? Well, flow rate is important because that's energy in the pipeline. As you increase the velocity in the pipe, then the water and oil tend to mix together. In most cases, depending on the viscosity and density, they will mix. So flow rate is a great stream conditioner, providing you've got it. Viscosity is your enemy. Viscosity, in a light condition, so the extreme could be, a condensate or a gasoline. Trying to mix that with water is almost impossible. So the lighter the product, the harder it is to mix. Therefore, the more energy you need to get it mixed. Similar with the density. And in today's environment, I've seen water cuts in the 30, 40, 50, 60, 70% range now in a lot of the production areas around the world. So it's scary how much water we're delivering. And when you're trying to mix, oil in water as opposed to water in oil, the whole problem becomes inverted, and it's much more challenging to mix more water in oil than less water in oil, if you see what I mean. And we have to worry about the droplet size, the dispersion rates, and things like that. There is something in the standards. I won't go into too much detail here because we don't have much time. But there's something called Annex A, which is a mixing ratio, and it's called the C1-C2 mixing ratio. And C1 is, if you imagine a pipeline, cut it in half or cut it down the middle. You've got C1 is the top, C2 is the bottom. What we're trying to do is get a unique, uniform profile ratio, a mix ratio from top to bottom of that line. And there's a very complex calculation behind the C1, C2. This might not look that way, but it really is. It's 4 or 5 pages in the standards of fanning frictions, Reynolds numbers, interfacial tension, all those things, important things that look at the ability with energy to mix water in oil in any given pipeline. And you can see here from the bottom axis there is the flow rate. So that's your energy as you increase the energy. This is a 20-inch pipe as an example with 0.811 SG viscosity 2 centistokes. So we've got energy or flow rate on the bottom. So the flow rate is increasing, and you can see then the C1, C2 profile, which is in the black, if you can see the color, the square rectangles, that's getting better. So that's climbing to the ultimate goal of 1. The limit we like to say is a 0.9. So we say C1, C2 with a 90% ratio is good enough to sample for representative custody transfer purposes. But the interesting thing is the blue line there, the smaller squares, that's droplet size, which is accessed on the right. So the droplet size, the water tends to cling together, that's dispersing and distributing across the pipeline. Therefore, the C1, C2 ratio is getting better. So there's a big complex calculation behind this, but this is a great way to see how, when you go to design a sampling system, what kind of energy you need. So in this case, on this particular example, my point here is 20-inch pipeline and these conditions, we do not meet the requirements for mixing. So we are wasting our time taking a sample from this pipeline unless we put a mixer in there. And that's the really important point from that slide. So in terms of a mixer, yeah, there's elbows, there's pumps, there's valves, they all produce mixing, you know, in the pipeline itself. But if there's not, if you've got a straight piece of pipe or a very challenging application in terms of its flow rate, density and viscosity, then you're going to have to add energy or steal energy. A static mixer is a good example of stealing energy. A static mixer is an element with a number of baffles in there, and I'll show you one in just a second. But that's stealing energy from the pipe to create obstruction, shears the oncoming flow to create mixture. And there's good things and bad things about static mixer. There's also a paddle mixer. I don't see too many of those in the world, but that is a good example of maybe a tank mixer. And then there's the jet mixer, which is what I'll be focusing on today, where you're adding energy to the pipe using the external pump there. You can see that pump at the bottom. That's creating a small slipstream and then blowing it back through a nozzle in the pipe through jets to create this big curtain of mixture. So the static mixer is absolutely usable. It's typically used in smaller pipes, although I've seen it in very large pipes too. But the turn down, so that its effective range is fairly limited, because there's one huge setback is the pressure loss. It's stealing that energy. So you size that static mixer to mix the contents of the line at the worst case conditions, again, which will be the lowest flow rate, the lightest viscosity, lightest density. The problem is it stays there, right? So next time around, when you ramp up the flow rate or when you go to the maximum best case conditions, as opposed to the worst case conditions, your pressure loss there is phenomenal. And that is energy, that is flow throughput, that is all the bad things you don't want the operator to have to bear with. So you have to be very respectful, very careful with the application of some of these. They're absolutely fine. They're not particularly efficient either. I mean, they do create mixture, but it's not a tight mixture, as I would call it, not an emulsion, but it's not a tight mixture. You'll notice the water droplet size is small, but it's not small enough in my book if you really want to hit the holy grail of the acceptance criteria we mentioned at the beginning of this presentation. So the other option is jet mixer. As I said, from right to left here, you've got a slipstream, a small slipstream, typically 2-3 inch maybe, going through a pump there on the left and then through the jet. So when you turn it on, it's sucking through a small portion of the main line, just a small portion, not all of it, and it's blowing it through the jets to create this pattern, this curtain of mixed product downstream of the jet. And the efficiency of this thing is much, much better. So your droplet size, and this has been proven, are in microns, not millimeters. They're very, very small droplets, water droplets, and they're dispersed and distributed across the pipeline. So your C1, C2 ratio that we talked about top to bottom is much, much better. Therefore, you can hit the acceptance criteria that we mentioned at the beginning of this presentation. And the big thing is, here you've got no pressure loss, right? You've got this nozzle sticking in the line with jets in it. There's hardly any pressure loss across this compared to a static mixer. So very important. So we've mixed the contents of the line. So we've done our hardest job, I feel. Now we need to take a representative sample. So that's the next step. So we take a sample using a composite sampler. They're taking small samples as frequently as possible to get representativity. Just get a drink here. So we're typically taking about 10,000 grabs per batch at 1 cc. Typically, I mean, it can change, but so it's very frequent to get that representativity. We don't want to miss anything. So each grab must need to be repeatable. So any changes in pressure, viscosity, we cannot change the grab size because it would not be deemed to be representative. We're taking it from the center of the line, and then we must take enough sample to the lab to be analyzed. And sometimes they like to measure density, water cut, viscosity. So it's typically 1 to 5 gallons in terms of the receiver size. And then, so we've mixed the pipe, we've taken our sample, now we take it to the lab in a receiver. And that receiver can be many shapes and forms. It can be low pressure if the crude oil is fairly dead, you know, it doesn't have high vapor pressure. If it's a high vapor pressure crude, you probably want to put it in a high pressure receiver. Then there's fixed receivers that sit in the field. So there's many different flavors of types of receiver, and you have to worry about how much crude you're going to take and whether they want to be fixed or portable. So there's lots of different flavors, but they're all doing the same thing. They're collecting a sample and maintaining it at the process conditions. You do not want to deteriorate the quality of the sample you've just taken, because that would go, against the whole objective of the representative sampling objective.
Hi, Gary.
Yes.
Yeah, this is Ahmad here. Just a quick question. I mean, you have mentioned that we can revert back the mixture to different pressure within the process, right? Can we, I mean, can we bring it back to reservoir condition? Kind from where it's coming from, sand phase.
Well, it depends on the
customer asks for that.
Yes, you can do that. So the high pressure receiver, if you've got an application that's high pressure, then you would use a high pressure receiver so you don't get any displacement of pressure. So you can transfer your sample from process conditions at roughly the same temperature and pressure into the sample receiver, so you don't deteriorate that if you need to do that. Obviously, there's limits with that. When you get up to the 10,000 PSI range, you're going to have to worry about HSE and things like that. So there's particular precautions around that. But generally you can do that.
Thanks,
Thank
Garry.
you. And then analysis. So analysis, once we've taken our sample to the lab, it's up to the customer, the lab, whoever's taking the analysis. But there are some rules around. Let's not contaminate the sample, manually or by man and ruin the representativity. We have to worry about what method we're using. Lots of people like Carl Fisher because it's easy. It's a chemical method. Other people like centrifuge, which is you're putting in a machine to spin the water out of the crude and then put it in it will be in a vial. You can measure by eye the quantity of the crude versus the quantity of water. And then storage and retention. I guarantee you there's arguments, right? If a ship pulls in and it's got $50 million worth on, and you deem it to have 1% water in there, $200,000 or whatever the number is in today's world, there's going to be an argument. There's going to be a dispute. So if you have retention, then you've got a referee. You've got a piece of evidence there. You can put on the shelf, I don't know, for 3 months, 6 months, put a label on it, preserve it properly, of course. And then if it goes to a court, a dispute, then you've got a referee, a piece of evidence there to work on. So all these things are really good ideas for the customer to make sure, or the user, the producer, to make sure that you've got your risk minimized, because this is all about reducing risk. And then proving. So proving is a really interesting, and if you're not familiar with this, it sounds very obscure too. So how do you prove that a sampling system is detecting all of the water that's going past it? Well, there's lots of reasons you do it. Return on investment, making sure you've done your job right, peace of mind knowing it's working, accountability, so meeting the standards if there's a regulatory a requirement on you. Improving it, you might want to look at what you were yesterday to what you could be tomorrow. Ongoing verification, so the standards now talk about an annual verification, or actually 3-year verification in most cases. And you might have a commercial obligation on contracts. There are 2 tests. The first test is 8.3, which is the lab test, to make sure your equipment in the lab is capable of measuring water in oil. So it will be the person, the receiver, and the analysis equipment, right? So that's really easy, and labs should be doing that all the time. If they're measuring water in oil, they should be doing an 8.3 test, a lab test, all the time, and it's fairly straightforward. The 8.2 test is the complicated one. So the 8.2 test, and you're not going to like this idea, but the only way really to do it, I mean, you could do through simulation, CFD, things like that, but you never really know until the sampling system's in operation on real life conditions. But what you do is you inject water upstream of the sampling system. You physically push water in the pipeline using a pump and a connection and a hose. You will put, and it's typically about 1% you will add over the baseline. You'll add 1% of water by volume into the upstream side of the sampling system, and then you'll run the sampling system to detect that water that you've put in. And while you're doing that, you measure the quantity or the flow rate of the oil, and you measure the quantity and the flow rate of the water. So you know mathematically what the ratio should be, how much water you put into the upstream of the sampling system. Now, the thing you don't know is something on here called baseline. So baseline is the normal water that's in there without injecting water. So you have to establish a baseline, which is you have to get a stable baseline. And then what you inject, you add what you inject to the baseline, and you measure the baseline before you do the injection period and after to make sure it hasn't changed. And then you will go to the you actually do 2 test samples, 2 test runs. You inject the water during each of those runs, and then you go to the lab to make sure that what you measured in the sample receiver equates to what the calculated theory number is with your mathematics for the ratio of the injected water metered versus the oil metered. And there is a procedure in 8.2 and ISO 3171. And there's a table, and I've just copied and pasted one of the tables from API 8.2 there. So if you inject 1%, as I said before, you're allowed plus or minus 0.15% of that 1%. So you're allowed to miss 0.15% of that water, in other words, and still be acceptable when you're using tank gauges. It's a little less when you're using custody transfer flow meters for oil measurement. So my point here is there's a very good method, or I say very good, there's an established method for proving a sampling system to make sure it's installed correctly and running correctly. But there's still a lot of room for improvement there, right? If you're doing, as I say, if you're doing 4 million barrels a year through your sampling system or to your refinery, and you're missing 0.15% of that water, that's a big number. At the end of the year, you know, it's hundreds of thousands of dollars of loss, because it is loss. So the standards set a benchmark, but I don't personally think, I think we can beat that benchmark, providing the risk is high. You know, it's a risky type environment where you're losing potentially a lot of money. So what I want to show you here is just the different types of sampling systems and the tests that I've done through the years, and show you what kind of performance of the proving tests. So the first one is an inline system, and this means the sample probe is in the line. This is a very basic traditional method. Putting the probe in the line, and then the sample probe then delivers the sample to the sample receiver, and you've got a mixing system here. Now, of the inline sampling systems that I've seen in the past, they're all over the place. You know, they're okay, but they're not brilliant. They're scattered. We see about a deviation of about, what was it, 0.118%. So from that 0.15%. So they're acceptable, but they're not brilliant. So, you know, I think they have a purpose. They do very well for that purpose, but there's still some room for improvement there. And we still supply a lot of these. They're still absolutely, they're on the menu. You know, they're a matter of choice. We are not condemning the inline system. It's just, it could be improved depending on the situation. And interestingly enough, that mean error there, if you can see that, this is the zero difference between what was expected and what you got in the lab. So that's the difference. And you can see the mean of these results that I've plotted here is about a 0.1. So that's the number that I'm saying here, that 0.11% away from zero. It's always a negative bias, which is really interesting. So they're performing okay, but they're not brilliant, is my conclusion to this. The other type of system is what we call a fast loop system. So you have a mixing system, but instead of the sampler being in the line, it's now in the cabinet. So you see the cabinet there. Don't know if you can see my mouse still, but in the cabinet, the sampler resides inside, and it sits above the receivers. And we've got a much bigger takeoff in the line, is what we call a takeoff. It's not a sampler, it's a takeoff that's feeding through that 1-inch loop for the sampler in the cabinet. So we're getting much better representativity now. Now I've got fewer of these numbers because I don't see many of the fast loop on their own, and I'll show you why in a minute. But that bias is much less. It's about half as much as it was, and the span or the scatter there is much more reduced. So we're sitting about a 0.05% from that error, which is really much better news. And these are actual results, remember. And then the final system is the COJETIX. So this is always installed on the high risk applications, the big ones that are moving a lot of oil. They've got a lot of financial risk to them. They're more expensive, absolutely, but they're bigger, but the result they provide is much better. And the difference here is we're combining the jet mix, which I showed you earlier. So you can see the jet mix nozzle here and the jet mix quill, which is downstream of that. And then we got the mixing loop as well as the fast loop combined. That's why they call it CO. It's a combination of the jet mixing system with the fast loop. And then we're getting the much better results. We're getting more results for these because these are widely used now. And they're arguably on more arduous applications because they're on the bigger pipe sizes, the wider density and viscosity ranges, but they're doing much better. And the mean there, the relative mean between the actual and the lab measurement is actually 0. It's nothing. So it's a much better result for those type of applications. And it's all about the representativity, the mixing number one, and then the representativity of the takeoff to the delivery of the sampler. And over the years, just to show you this slide quickly, over the years, and it's been the jet mix has been around many years, and we've made everyone has made lots of improvements to that design. They went from a couple of jets to plural jets, 14, 15, 16 jets in a pipeline. And we've used CFD to help us model the geometry of those jets and point them in the right direction. So we've made a lot of improvements over the years in these things. And this is all proving numbers, right? This isn't theory. This is actual proving results in the field using real life conditions. And just to give you one final example here. So this was actually in California at BP. And I actually did this test. So it was on the left an original inline system, you can see sitting there, and we changed it to a COJETIX system. And we ran them both for 3 months just to see what would happen. So we didn't decommission the old one. We kept it going for 3 months when the new one was started up. And during that period, they moved 25 million barrels of crude oil. And we found 21,000 more barrels of water in that crude. And at the time, I forget what $70 a barrel, it's there. So at $70, that's $1.5 million in 3 months, finding more water in the new system versus the old system. And, that's the kind of losses that we typically see. And that's why it's so important to do quality measurements so well and not just look at the standards, but go beyond that from a return of investment point of view. Something probably dear to your hearts is control. So, I like to see a good control. I love to see feedback from a sampling system. You could do this with a PLC. There's no magic in this. It's just having the programmability and configurability of these things. But, the alarms, the reports, just being able to go in there and configure something as opposed to programming it. There's many different features you can have. And having we have a mass weighing system in the field, so we can look at the accumulation mass of the sample in the receiver and compare it with the expected. So we run a performance factor, which is really important, and that's in accordance with 8.22. And you can add diagnostics in there and things like that. So I think the sample control is really, that's the important governing thing, taking samples proportionally with flow, making sure they're spaced out and having the feedback from the field all at once. So I've seen it done many different ways, but this is quite an economic way of doing it because it's all purpose built. And then a typical layout, I don't expect you to read that, but I'm sure you can attest to, P&ID drawing like this. So you can see it's quite complicated from a high-end system where all the control points are and you're controlling solenoids, you've got safety to worry about, the feedback from the receiver. As I said, you've got a load cell under each receiver feeding back the weight of the receiver, and the weight of the receiver is important for two things: performance measurement, as I mentioned, but also safety. You do not want to start a sampling system without a receiver in place because you will put oil on the ground, and that's very bad. and you're controlling pumps and strainer differentials and things like that. So there's a number of control points on there that you need to think about. And everyone's a little bit different. I wish there was a cookie cutter sampling system, but there really isn't. Everyone's always a little bit different. And one thing I didn't mention was you can add densitometers, viscometers on the fast loop of the sampling system too. So you can have online information, online density, online water cut, online viscosity coming back to the control system. Now, so getting into the meat and potatoes here was the smaller pipeline sizes. So, what if you've got a small line size, 3, 4, 6, 8 inch, which most of the North Sea is when you look at it offshore there, it is that kind of size. Very rare you get above that unless it's a major gathering point. So how do you mix that without intrusion or pressure loss within that line? Traditionally they've used static mixers, and that's been really difficult because of the RVP, the reed vapor pressure of the products. Typically, they're running at very close to RVP pressures, and if you add a differential in there, then you're breaking out. The product is you get a gaseous phase breaking out because it's so near to the RVP pressure. So we come up with a very unique way of using the JetMix technology. Instead of sticking a nozzle like we would do, like I've showed you originally, we are creating this jacket around the pipe, as you can see up the top, and I'll show you a slide in just a minute. But instead of putting that nozzle and jets inside the pipe, we're putting it around a jacket, around the wall of the pipe, and spraying it from the outside in, around the circumference of the pipe. And this way, we get absolutely no pressure loss, no restrictions, because if you put a jet in there, if that's a 6-inch line and you put a jet in there of 3 inch, you've blocked that line by half. You put a static mixer in there, you've blocked it by more than a half. So the pressure loss and the potential for gas breakout is massive. So we've come up with a very simple configuration where you have a jacketed jet geometry around the wall of the pipe. It's spraying inwards, and then you're having your suction, and then your sampling system is exactly the same as it was. So it's a much easier operation. And here there's a rendition there, a CFD of how that works. So you've got your jacket around that in the lower diagram there, and in the upper diagram you can see the cross-sectional area where that jacket is, and you can just see the jets that sit around the wall of the pipe that are spraying it inside to get that pattern, that creation of mixture, homogeneity within the pipe, so you can take that representative sample. So when you compare the JetLine efficiency with the mixing, it's quite dramatic. On the left there is the C1, C2 calculation that I run, and you can see that's what is that, 8-inch piece of pipe, and the red line is a static mixer. So that's doing a really good job in terms of mixing it. The problem is, again, as I said earlier, you have to size that static mixer at the worst case conditions, which will be your lowest flow rate, your lightest density, lightest viscosity. The problem is, according to and when you look at that on the right, the pressure loss is phenomenal when you get to the high side. So, an operation, number one, you're going to get deficiency in flow rates because of that pressure loss. Number two, it's going to cost you an arm and a leg in energy to overcome that pressure loss, if you can overcome it. And number three, you're going to get this gas breakout, which is disastrous for measurement in any phase. So static mixers are often ignored because of that reason, and therefore you don't get any mixing, therefore your sample's not representative. So the JetLine really solves that whole problem because it's got no pressure loss, and its turn down, its rangeability is very high. A few years ago, we took this to National Engineering Lab in Scotland. I actually went for one of the tests, so it's really exciting to be there. And it was in their old facility. I think they've got a new facility, and if you ever get the chance, go there. It's a brilliant facility for all kinds of things. But we ran a JetLine on a number of tests, and we did high water. I'll show you the results in a minute. And we had a perspex chamber there. We could actually see what was happening, because it's really unusual. You can never see inside a pipe, right? But they had this piece of perspex section that we could actually see the differences as we increased the velocity of the flow through the jet line. You could see the differences in the way it was picking up the water and mixing it very thoroughly, and then we were sampling downstream of that. So we ran a 6-inch because that's what we had. So 6-inch, it was the NEL test oil, and we ran up to 32% water because that was about their limit. But it was a great test in that respect, and we did about 0 to 2 meters a second in terms of velocity, and then we varied the velocity through the loop of the jet line too, changing the velocity through each jet to see what the optimum speed was, or optimum velocity for each of the jets through the shroud. We had some mixing calculations going in. So this was our design criteria. Again, this is the C1, C2 calculator I told you about. So we did the calculations of what design it should take, how many jets, what size they were, and what direction we wanted them pointing in. We looked at the cone of uncertainty for the droplet size. Everything kind of looked correct. And then we came back with results, and I know you probably can't read this, and I just wanted to show you, we did a lot of results in a lot of different ways, different water concentrations on the second column with different velocities in a different orientation too, on the same oil, but lots of different water concentrations, up to 32% water, and in different velocities too. But basically, on this chart, you can see the total water on the bottom versus the error on the left. So this is if you look at the dotted line, that's the NEL uncertainty that we expected. The blue cone is the ISO limit for, and ISO is the more stringent out of the two, by the way, API versus ISO. So we went for ISO. So we were well inside the acceptance criteria. And in fact, we were much better than that. So I was really pleased with those results, even up to 32% water. You know, measuring 32% water at that kind of uncertainty is really challenging, you know, in a pipe that size, you know, with that kind of analytics behind you. So it was pretty rewarding to see that. So it's a really good solution with no pressure loss. And this was the kind of conclusions. We ran it up to 14 meters a second. We were grade A pass, which is the best pass in ISO, at any velocity and any of the water cuts or water percentages we did. And we went to the 8.22 and we tried different orientations with or without a takeoff quill and different returns. So it was pretty pleasing to see that. And since then, just to conclude, because I know I'm running short on time here. Just to conclude, so we've deployed a number of these. I chose a couple. There's one here in Alaska. We put a couple of systems in for light hydrocarbons with JetLine. That's inside because it's Alaska. It's inside a building that's all insulated and heated because of the winters they have there. But it was all modular, and I think that was an 8-inch pipe for BP. This one is a North Sea, a very similar application. You can see here in the cabinet, we've got a water cut meter there on the left. That is a phase dynamics microwave water cut. So we are measuring online water cut. There's a densitometer in there somewhere that I can't see from looking, but there's a densitometer in there somewhere, probably the Emerson. Oh, there it is. It's just next to the water cut device. It's laying vertically, but that's a compact CDM, compact density meter. Again, light hydrocarbon with high RVP, so we had no opportunity there to go past the RVP point. So we had complete restriction on the pressure loss, and therefore minimized or zeroed out the opportunity for any gas breakout. And I think this was Neptune in the North Sea. So this was an interesting recent project, actually. Again, high RVP. You can see the two densitometers sitting there in the cabinet on the left with a water cut meter just to its right. And then these were the fixed sample receivers. So they've got their own mixing system. So they're captured into a high pressure sample receiver because of that high RVP. But again, a JetLine in the main line sitting at the bottom there, and then feeding these to analytical or quality cabinets with online water cut, online density. So sorry, I'm a couple of minutes over time there, but my conclusions are quality is as important, if not more important than quantity. The standards follow some excellent guidelines and break it down for you how to design a sampling system to get that return on investment. The biggest bane for me is always mixing. You know, if you haven't got your mixing correct in your main pipeline, you are wasting your time and money after that. Pressure loss in the main pipeline can bite you for all the reasons we discuss, particularly in small pipelines where your products are very high in RVP, condensate-like, and they've got the potential there to boil off, and that will cause all kinds of measurement and operational problems. Certify and prove the system. Don't take my word for it. Always prove the system. It's not the best test in the world, but it's a test and it's stable and it's been around for years. We know it works. And then obviously don't apply all these rules to everything. Only apply the rules of the high-end type duty sampling systems with low uncertainty to the risky ones, the big ones that will, lose you money. If it's, as I said before, if it's a mom and pop type operation, few barrels a day, don't bother. But if it's millions of barrels a year and your contracts are written around losses, then absolutely apply everything you've got to make sure we minimize loss. So thank you very much. I hope you found that interesting and relatable, and I'll gladly take any questions I can possibly answer. And if I can't, I will get back to you.